What if we could harness limitless energy? Picture a world where the power of the stars is at our fingertips. This isn't science fiction, it's the promise of cold fusion, a process where atomic nuclei fuse at low temperatures, releasing vast amounts of energy. Today, we're going to explore the complex concepts of the McGinty Equation and quantized inertia, key components in the development of a new era in cold fusion technology. The McGinty Equation, or MEQ, is a fusion of quantum field theory with fractal geometry. It describes how quantum fields behave in systems with fractal structures, patterns that repeat at different scales. These structures have unique properties that affect the way particles interact on a quantum level. The McGinty Equation helps us model and predict these interactions more accurately. But how does this tie into cold fusion? That's where quantized inertia, or QI, comes into play. QI modifies our traditional understanding of inertia by incorporating the effects of Unruh radiation, a type of radiation predicted to occur when objects accelerate. In the confined spaces of a cold fusion reactor, these effects become significant. QI suggests that inertia comes from the interaction between a moving object and this radiation, boosting the chances of quantum tunneling. This means particles can overcome barriers more easily, facilitating fusion at lower energies. By combining MEQ and QI, we create conditions where hydrogen nuclei can interact more effectively. The fractal geometry within the reactor's nanoscale cavities changes the potential landscape, reducing the barrier that usually prevents nuclei from fusing. Simultaneously, QI increases the likelihood of these nuclei tunneling through the barrier. This makes fusion possible at lower temperatures and pressures than ever before. The use of 28 nanometer asymmetrical fractal cavities is crucial. These cavities enhance the interaction between hydrogen nuclei and the modified potential landscape created by the fractal geometry. This innovative design is a significant departure from traditional fusion reactors, which rely on extremely high temperatures and pressures to achieve fusion. The experimental setup for this reactor involves advanced nanofabrication techniques to create the necessary fractal cavities. We use materials like palladium and nickel, known for their hydrogen-absorbing properties. The experimental apparatus includes neutron detectors, gamma-ray detectors, temperature monitors, and mass spectrometers. But how do we know it works? The empirical evidence speaks for itself. Consistent neutron flux measurements confirm that fusion reactions are occurring within the reactor. The observed gamma-ray spectra match theoretical predictions, indicating successful fusion reactions. Significant and sustained excess heat generation surpasses what could be expected from chemical reactions alone, and the detection of helium-3 provides further confirmation of ongoing fusion reactions. In a nutshell, the integration of the McGinty Equation and quantized inertia is revolutionizing the field of cold fusion. By harnessing the unique properties of fractal geometry and quantum mechanics, we're on the brink of a new era in sustainable, limitless energy. A world powered by the stars is closer than we think.